Okay, good evening and welcome back. It's already the lecture number 9, so we don't have so many more anymore, but we still have to learn many things. So let me remind you what we have done last week very quickly. I first mentioned what is an oriented manifold. It's one orientable, and we have seen what it is. And we have seen that whenever a manifold is orientable, it has two possible orientation. We say it's oriented when you have chosen one. You have two choices, you choose one of them, and it will play a role today. And when you fix one, in fact, it means you fix an atlas. So you fix a way to cover your manifold with charts, which preserves the orientation. So when you move on this atlas, a certain determinant is always positive, the determinant of the Jacobian of the transition functions. Then I explain how to integrate M forms. So M is a manifold of dimension M. We have seen that this is a maximal degree. After M plus 1, these kind of forms are zero. They are all zero. But if we take a form of degree M, which has support in one of these charts, then we know that it can be written locally as just a smooth function times something of this type. This is not very important, but it's a way to organize your computation. But what is important is you have only a function which is infinity with support in this u beta, and the definition of the integral of this M form on M, because phi has support on u beta, you can just write u beta instead of M, because elsewhere it's 0. And this is a formula which is important, but this is something of calculus 2, because this function is now a function defined on Rm. So you have M variables, and you do integral. I forgot to mention the integral is on phi, the image of u beta. So this is just an integral on Rm, okay, on part of Rm. So we have a definition for the integral of a M form on the manifold. And this is if the M form has support on one chart. Of course, sometimes you need more than one chart. So for a general M form, what you need is a partition of unity. So you define this integral of the M form on M with a partition of unity. And this partition of unity has to be what we say subordinate to the covering. It means you have your manifold, you take a covering of it by element of your atlas, and in each of them you take a function f beta which has support in u alpha, and you get something which is meaningful, and you add these different contributions. So you go from a very specific M form with a special support to a general one by adding different parts with a partition of unity. So these partition of unity are very useful. Then I mentioned Stokes' theorem. I don't recall the exact meaning of all these things, but what is important with Stokes' theorem is that for any form of degree M minus 1, you relate its integral on M of its differential. So here you have a form of degree M. You relate it to an integral of something on a manifold of the dimension n minus 1. And in calculus, we have seen these kind of things. You have a manifold, you integrate something on the surface, and it's equal to something on the boundary. So this Stokes' theorem is a generalization for any dimension of something that we have seen in calculus 2. It's called Green's theorem, Stokes' theorem, divergence theorem. Everything is encoded here. And the proof is not really much more complicated than the one of calculus 2. Now, you often would like to integrate just smooth function on your manifold. It turned out that there is no way to do it just with one smooth function because you have no measure on your manifold. The way you do it is you have to fix an M form, and then it turns out that this product is still an M form, and this is now meaningful with what I explained here. So in order to integrate a functional manifold, you need one more ingredient. However, this one, I will show you a special case today in the case of Riemannian manifolds. So in some case, there is a canonical phi. Finally, now we take a curve. So it's a parametric curve from an interval to M, and I call the curve with this capital C. If I take now a one form, I gave a definition of the integral of this one form along the curve. You take the pullback, and this expression is now a function on Rm. And no, it's a function on an interval. It's a function on AB, which has a representative as just a simple function. And this is an integral of calculus 1. So the integral of one form along a curve reduced to something which is back to calculus 1. Okay, now I want to state two properties of these integrals. If the one form is in fact obtained as a D of a zero form, because the D of a zero form is a one form, it turned out that this integral is just the evaluation of phi at the endpoint of the curve times phi minus phi at the evaluated at the initial point of the curve. And the second result is if you have a way to transform continuously one curve into another one on your manifold. So I gave a precise definition, but you can think about continuously deforming a path on a manifold. And if you take a one form which has a zero differential, so this is a condition, then the integral of this one form on the curve C1 is the same as the integral on the curve C2. So it means this integral is the same as this one. However, be careful, this does not follow from this result, even though for some cases it's a corollary, but for not always. And just at the end, I introduced Riemannian manifold, and today we are going to deal with Riemannian manifold. So it's just a manifold with a symmetric bilinear forms. So I introduced this. It means you have a two form or a two tensor field, and it has to be positive definite. I explain it, and we will see it today again. But what you should keep in mind, it's just at every point of the manifold, you have a matrix which is positive definite. And positive definite means something like this. Your matrix applied on a vector takes the scalar product with the vector itself. This is a scalar product of A psi, AXI, scalar product with xi. With psi, this has to be bigger or equal to 0. And it's positive definite if in addition, it's 0 if and only if the vector is 0. So a Riemannian manifold, you can think about it as a manifold with a matrix like this, which would depend on each P. It's a positive matrix at every P. And it turned out that such manifold exists, and we have many, because any smooth manifold can be endowed, or you can put a Riemannian metric on it, and I just sketched how last week. And it's not surprising, because a smooth manifold is locally like Rm. And on Rm, of course, you have plenty of positive definite matrix. And the simplest one is just the identity. So you can interrupt me if you have any question and at any time. Today, it's going to be slightly simpler because most of the things will be in Rn. So we will deal quite a lot in explicit space. So it's not an intrinsic presentation. But let me continue with Riemannian manifold. So for any Riemannian manifold, we have this Riemannian metric. So this Riemannian metric, I will denote it by phi. It is precisely an element of this which is positive definite, defines a scalar or an inner product, I should say, an inner product, but it's the same as a scalar product, an inner product on Tp of M for any T belonging to M. Because, as I just mentioned, you have a matrix, and this matrix defines an inner product. What is an inner product? It's precisely a map like this, which is positive definite. This is a generalization of inner product. But what does it imply? Linear algebra, whenever you have an inner product, you can construct a basis which is also normal. So we can construct an orthonormal basis on each Tp. You can do this because you have this scalar product. And how you do it, maybe you remember one name, it's called Graham-Schmidt. Schmidt. This is a way we construct also, I mean, there is a process which tells us how to construct an orthonormal basis. You start with one vector, then you construct a second one, which is also normal to the first one, and then a third one, and so on. So I'm going to use, I will not use it so often, but we call this, we denote this basis by FJP. From 1 up to F. And what means orthogonal? You have to be careful. It means that by P applied to FJP, FKP, take a different one, is delta JK. This is the meaning of orthonormal. It's based on this matrix, which is positive definite. Okay. However, just be careful about one thing. We had another basis, a remark. Given a chart, I just want to mention, given a chart which I call U phi, we had a basis which I denoted by EJP. And we had a formula for this. This basis is not orthonormal, but it's still a basis. The main difference is, be careful about this. This one, when you move P, it's moved smoothly. Because the way we construct, there is some smoothness. Now, if you construct artificially orthonormal basis based on this, but you construct an artificial basis orthonormal, it's not clear that you keep this smoothness. So you may have something which is not smooth. So I'm not going to say that this orthonormal basis has any continuity or any smoothness when you move on P. So just be careful about this. This one was constructed on purpose. This one is a bit artificial. But at least we know that we can construct on each tangent space a basis which is orthonormal. And this it's very useful for the next statement. And this is an exercise. If somebody wants to make look at the proof of this statement, it's very good. I will sketch something, but I cannot give the full proof. You remember just before I said when we integrate a function, a smooth function, we need to choose an M form. I told you in some cases there is a canonical one. So for Riemannian manifold, I'm going to mention more precisely this canonical one. So let M be an orientable manifold. Smooth. Everything is smooth. So it's a smooth manifold. For each orientation, and we know that we have only two of them, for each orientation, there exists a unique M form. Like this one, there exists a unique M form, and we usually denote it by capital omega. There exists a unique M form omega satisfying that omega. So it's an M form. I can evaluate it at P, and I can look at it at when I evaluate it at F1P up to MP. So it's an M form, so I can put there are M variables. When I put the M variables equal to these vectors of the canonical basis, this is equal to 1. And this is true whenever this F1 P up to Fm P is positively oriented. Orthonormal basis of the tangent space. Okay, so how to understand this? We have plenty of M forms. Now for Riemannian manifold, on every tangent space, we can define a basis, or many, but at least one basis which is orthonormal. And it turns out that, again, for Riemannian manifold, okay, maybe I should have mentioned, sorry. For each, let M be an orientable Riemannian. Otherwise, I'm in the chapter Riemannian, so so for each orientable Riemannian manifold, you can find a very specific M form, which has a property that when you put it on these M vectors, it gives you 1 for any orthonormal basis. And what means positively oriented? You have two orientations. If you fix one, all these bases have, we have two orientations, but it means they have the same orientation as the initial one. In physics, it appears often that you need to take in one orientation, because if you take in the other orientation, you have a minus sign which appears. And this omega is called the volume form. It's the M form, which is called the volume form, or the volume element. I emphasize this because it's a Riemannian manifold, so you have the manifold and the Riemannian metric. What is the idea? As I said, I cannot prove in full details, but let me give you the idea. Take a local chart. I always call it U phi. So you have your manifold, you take a U and you send it to a part of Rm. This is part of Rm. So take a local chart and set Dij at P is the following thing, pi P of E minus T E J. This is well defined because we have seen whenever we have a chart, I already mentioned it just before, we have a certain basis and we have expression. These vectors are part of a basis of the tangent space. And precisely this Riemannian metric, it has two variables on the tangent space. So you put inside, you apply this two tensor field on these two vectors, and you define this. Observe that this is just a number for each for I and j belonging to the set 1 up to m. So this is just a number. Okay. But if you do this for all ij, it means you have a matrix. Because if you have a family of numbers indexed by I and j with I and j in 1m, you have a matrix. So it turns out that this Gij of P, when you look at it as a matrix, is a positive definite matrix. And the way you prove this is precisely you have to use that there exists an orthonormal basis. So in the proof that, it's not a difficult proof, but in this proof, you use this orthonormal basis because you have a canonical way to express any vector in this, and then you show that this is a positive definite matrix. So this is the first ingredient. Okay, no, I'm saying something wrong? Wait. No, probably I'm saying something wrong. Sorry. It's a special case, but no, sorry. I said something wrong. This matrix has a positive determinant, sorry. Which is true for definite positive matrix, but probably you have matrices which have a positive determinant which are not positive definite. So sorry, it was a mistake. This, you compute its determinant, and it turned out that it's strictly positive. Strictly positive. It's strictly bigger than 0. Sorry, I made a mistake. Okay, and yeah. No. This one is the one you obtain with a chart. No, the definition, no, it's not at all an arbitrary one. We have an expression in fact, we take a basis on Rm and we push it on the manifold with this phi. So no, we have an explicit expression for them. And we define this with this basis. But it turned out that, yeah, this matrix has a positive, strictly positive determinant. And then we set this phi star of omega is root of Okay, what is the meaning of this? This function is defined on the manifold. This one goes from okay, let me do it again. It goes from Rm to the manifold because the manifold is here and phi is a local chart, so phi is going in this direction. So its inverse is going in this direction. So we take a point here, we apply phi minus 1, we are M. Then we look at this matrix and we take its determinant. So by what I said, this is strictly bigger than 0. And why is it? So I take this one, which I haven't defined. We say it's in this, but I define its image through this pullback. So its image is here. Why is this one important? Because remember, when I defined the integral of phi, which was, this is of M form, when I defined this, we had to bring this back to Rm. And it was a usual integral on Rm. So the important object is this one, because this one lives on Rm. So this is the one you need when you do the computations. So we define phi by its image through this pullback. It gives us a way to compute the integrals on the manifold by formulas on Rm. And it turned out that you can check this with this definition. The phi has a property mentioned here. It's part of the computation. Yeah. No. So no, Gij, be careful. Gij at P is a number. So I first take a point here. I take it back on the manifold. Now I am at a P. I compute this matrix at this P, and I can take its determinant. So no. I do not evaluate. In fact, here, this is, altogether, it's a function. It's a function. It gives me a certain weight. When you do a Riemann integral, remember, when we integrate on interpretation of a Riemann integral is you give a weight of, or a density. If you have a density, when you integrate, you take the weight of this small and then you add everything. This guy is exactly the weight that you give at each point on your manifold. So this is your manifold. In a sense, you decompose into small parts, and this guy gives you the weight of each part, but you send it to Rm because this is where you know how to do an integral. You should think about it like this. Okay, so this is correct. I missed the parentheses. In fact, it doesn't really matter if you put the parentheses or not, because you can either take the determinant and the P then is the inverse image of X, or you first take this expression and then the determinant is the same. You have another question? No, this is because this is a number, and I usually, when I want to describe a matrix, I just recall Aj from 1 up to M. Yes, if you want, I can accept that. Okay, no, you're right. If I want to be coherent, I should do it like this. Okay, it's better now? Okay, maybe I should correct in the notes then. And this expression is a name, or has a name that we often see in differential geometry. This expression altogether after the determinant, so I should add this here. This is often called the G in general relativity. But now we have a special volume form which is unique, and we can use it to remark. We use this volume form for precisely defining the integral of f Now, instead of taking an arbitrary M form, I'm going to use this one for any smooth function on the manifold. So I told you for Riemannian manifold, you have a specific one. And it's unique. And you can see the uniqueness by construction. It's explicit, and then you observe that it has a good properties. All right. Again, if somebody, the details are not very complicated. It's how to show that it has a strictly positive determinant, which has to be done, but it uses this orthogonal basis, orthonormal basis. Now I want to define length. I want to define length on the manifold, because we have our manifold, but we don't have so far any notion of length. But for Riemannian manifold, we can do it. So we consider first a curve, a smooth parametric curve, a smooth parametric curve. So what is it? It's just C from, I take a closed interval, but last week I also mentioned it's not so important, to M. And so we have something like this on the manifold. And the tangent is given by C dot of T, which is by definition, be careful, C star of D over dt at T. Why I recall this? Because if the manifold is not in a bigger space, we had to give a meaning of the tangent vector, and this was the meaning we gave. This is an element of T, C of T of M. It's an abstract version of what you would draw on this picture as a tangent vector. But now, definition, I want to define the length of this curve. What is the length of this curve? Probably in calculus 2, we did it, but in RM, so definition, the length of this curve is given by the integral on AB of phi C of T, C dot of T, C dot of T, 1/2 it. Let's check that it's meaningful. Phi is our metric, Riemannian metric, so we evaluate at one point, at this point. And a metric needs two elements, which are two tangent vectors. So we put two tangent vectors, exactly these two. So it's meaningful. So it's a definition, the length of the curve C, which I have shown. Remark, and this is an exercise that we do in calculus 2, but in a slightly restricted framework. This length, or L, does not depend on the parametrization. What do I mean by this? Take the same picture. So C is this altogether. This is C. Now you have different ways to work on this. You can go very fast or you can go very slowly. It's a different parametrization. It turned out that what you compute will be the same, which is what we expect. It should only depend on the curve itself. And one more thing that I need to introduce, which will be useful later, the arc length. We also set the integral from A to T of phi C of, be careful, change the variable, because otherwise you it's not meaningful. So I not integrate from A to B, but from A to T is called, this is called the arc length, and it will be useful later. And we usually, it's a function of T, so we usually denote it by S of T, or T between A, of course, if it's A, it makes 0, and B. And if it is B, it makes L. And just one notation which is often written, also written. So this is a precise definition. We know everything, we have it. But it's also written ds over dt, where is pi c of s dot s dot. And you can understand this notation. This is not a okay. The meaning of this is indeed, if you differentiate with respect to t, you differentiate with respect to t, so you have this evaluated at t. Now, if you take the square, you indeed get just this expression. So it's meaningful, and often we see this expression, but the meaning is here. So we know how to define the length of a curve. Why is this useful? Because I can now define a distance. I want to look at the distance between P and Q on the manifold. So how am I going to do it? I'm going to consider all curves. So take 2 points on this manifold, here and here. I'm going to consider all curves which go from P to Q. And then I will take I can compute the length of each of these curves, and I'm going to take an infimum. And it's going to be meaningful because at most it is 0. So you have an infimum which exists because it's bigger than 0. This is the way we are going to define a distance on the manifold. So if you have any question, of course, you interrupt me. On the same online. Martin, if you want to ask a question. For P and Q belonging to M, I'm going to define the distance between P and Q as the infimum over all L. And what is L? L is the length of a curve, of a smooth curve between P and Q. So you take all of them, you compute the length, and you take the minimal length. Clearly, what we observe is that d of PQ is either positive or 0, because the length is always positive, but also d of PQ is the same as P of QP. Because going from P to Q or going from Q to P, you have the same curve. Oh, yes, thank you. D of QP. These two properties maybe remind you something. What is a metric? Or what is a metric space? It's a space having something which is of this type. So let me remind you what is a metric space. It's something where you can measure, because there is a metric. And so I record something, and it turns out that a manifold is a metric space. So this is a reminder, or maybe it's new for most of you, but still it's a reminder. I consider M and D. What is M and D in this case? M is just any set, and D is a map from 2 copies of M with value in R. So it's a function taking 2 points in M n with value on R. This is a metric space. I give you a definition if there are four conditions. First, you want to have the D of PQ. No, maybe I don't use PQ because this is just abstract. So I can use XY, D of XY has to be bigger or equal to 0. You want a distance to be bigger or equal to 0, and you want equality. Oh, it's already the second condition. 2, we want D of XY equal to 0, meaning X is equal to Y. This is the second condition. The third one is that D of XY is the same as D of YX, because there is a priori no reason why it should be true. If D is just a function from M times M to R. And we want to have the triangle inequality, D of XZ smaller than D of XY plus D of YZ, which is something you should be familiar with. When you have 2 points, the distance, I'm just trying to write an abstract version of a distance. The distance between X and Y is always smaller than I took Y, X, and Z. The distance between X and Z is always smaller than the distance between X and Y plus the distance between Y and Z. This is called triangle inequality. Triangle inequality. While the third property is called the symmetry. Symmetry. It's a symmetric relation. Symmetric relation. So this is a metric space. It's a set, a function from 2 copies of this set to R, satisfying these 4 properties. Now we have seen that the D I introduced here has already property 1 and property 3. So you can wonder if property 2 and property 4 are also satisfied, and the answer is yes. And this is a theorem which said that this D I have defined, so it's a theorem, any connected. I need to be connected. Why? Because if you have a manifold made of 2 parts, you cannot consider the distance between these 2 parts. But any connected Riemannian manifold is a metric space, with D given by what I have written there. It's a D given by this expression. So it means condition 1 and condition 4 are also satisfied. But you can say a little bit more. Maybe I should have mentioned before. When you have, okay, keep two lines here, because I will add a sentence, but in order to explain it, or to explain this sentence, I just need to do something. When you have a distance, yes, you have a question.
Property 1 is satisfied even if the manifold is not Riemannian manifold.
How do you define the distance if in the notion of distance, I have the length. The length is based on the Riemannian metric. So if it is not Riemannian, probably you can still do something, but I'm in the framework of Riemannian. So yeah, the D is defined only with what I have introduced. It's only defined if you have a Riemannian metric. But when you have such a distance, what can you do? You have balls. So observe, it's an observation. I will finish the statement in a second. Observation with a metric. We can define balls. What is a ball? Ball centered at x and of radius r is nothing but the set of points y in M, such that the distance between x and y is strictly smaller than r. R, of course, is a number bigger than 0, and x is an element of M. So whenever you have a metric space, you have maybe they are not very, they do not look like ball. It depends on D. And in calculus 1, yes, we have seen some balls which have this shape, but still you have this notion of balls. And if you have balls, you have a topology. So it means, in particular, it implies that metric spaces are topological spaces. Because you can define the notion of open like you do it on Rn with balls, and it turns out that this defines a topology. So any metric space is a topological space. So it means with this distance, we can define a topology. And then you can wonder, oh, but on our manifold, we had an initial topology. So now we have two. One, the initial one, and one constructed with this distance. Are they the same? And the answer, of course, is yes. This is the second statement. The topology defined by D correspond to the initial topology only. You know, if this wouldn't be true, we would be a little bit annoyed because we would have an initial topology, and suddenly for Riemannian manifolds, we would have a second one. And if they do not coincide, you would have to specify which one you talk about. But no, the topology given by these balls correspond to the initial topology. So no problem, no surprise. Now I will finish this section very soon, but there is one name that I need to mention, is one theorem in this framework. But I just write a few lines. So, do you have any question? So the good point with Riemannian manifolds, we have this notion of length. And with this notion of length, we define a metric, and metric space are good because you can measure the distance. So two Riemannian manifolds, M1 and M2, we call them isometric. I call isometric if there exists a function or map from M1 to M2 such that the distance between P and Q is the same as the distance between F of P, F of Q for any PQ belonging to M1. So it means we say that they are isometric, so you have two manifolds. If when you have 2 points is whenever you have PQ, if there exists F, so that when you measure the distance between P and Q on the manifold, it's the same as the distance between F of P and f of q. This is called isometric. And there is just may mention this condition that it preserves the norm can be written slightly differently. It is E2. This is equivalent. It's just a shorter version of it. And now there is a deep theorem. I have no idea how to prove how is a proof, but it's a rather deep theorem. It's called Nash embedding theorem. Nash embedding theorem. You know, I always draw the manifold like this, but in this picture, it's like if the manifold is inside something, inside the blackboard, which is two-dimensional. But I gave an abstract definition of the manifold, but this Nash embedding theorem says every Riemannian manifold can be isometrically, this is important, isometrically embedded into n for n large enough. So what does it mean? It means I gave an abstract definition of a manifold. You can always put this manifold in a big ambient space. So you can always put it in a Rn. But it turns out that this n is usually very large. So it means for any interpretation, this is not so good. But still, it said that any Riemannian manifold can be seen as a manifold inside Rn. And this embedding is isometric, which means the distance in the original manifold is preserved on its image. And as I said, it's not at all easy. But at least you can understand, we know what is an embedding, we know what it means isometric, it preserves the distance between every point, and every manifold, Riemannian manifold, can be put in a big space Rn isometrically. Any question or remark? Yes?
So do n has to be finite?
Yeah, there is even an upper bound for n. No, R infinity doesn't mean anything. So n is finite, of course, but it's a big number. And, you know, you can even express n as a function of m because your initial manifold had a dimension. So there is an expression of this n in terms of m, but it's a big multiple of m. And there is a game trying to find the minimal n, and I think we know that there exists, we have an upper bound, and we know that you cannot go lower. There are counterexamples. No, people have worked a lot in this direction. Okay, that was the complicated part for today. Now something rather easy, which in a sense should have been done in calculus 2. But okay, because it has not so much to do with what I introduced up to now, but it's important to know this. It's going to be something related to a curve in R3. So I want to present it because it's something you will probably meet one day or see one day. But again, it's much simpler than what I have introduced to now. So we consider, so I can go slightly fast. We consider a curve AB in R3. It's a three-dimensional problem. C is regular if C dot at any t is never 0. And here, we are in R3, so it's just the derivative of this function. There is nothing special. If this derivative is never 0, be careful, this is a vector in R3. We say it's regular if it is not 0 for any t. And this is important because if it is 0, it means you are going to stop at a certain point. I don't want to stop. Lemma. If C is regular, calculus 2, if C is regular, there exists a diffeomorphism, maybe even first lecture of calculus 2. Oh, probably you had this statement, diffeomorphism phi from 0L to AB, so that when you compose C with phi, take its derivative, take the norm. This is a vector, and you take its norm. This is always 1 for any. I need to evaluate at one point. This pointing is going to be a S because it is the arc length for any S in 0L. And we did it in calculus 2. We can reparameterize the curve such that its derivative is always of length 1. It's called the arc length parametrization. Okay, so I'm going to set T of S as C composed with phi evaluated at S. It's a definition. I just take this. Of course, it's of length 1. The length in this case is just the usual length I have in for curve in. Oh no, this is a length of as a vector in R3. Okay. Observe. 0 is the derivative of a constant 1, which I'm going to write as a derivative d over dt of T of S, T of S. Why? Because this scalar product is precisely the norm square, but the norm is 1, so it's a derivative of 1. And the derivative of a scalar product makes T dot of S times T of S plus T of S, T dot of S. Dot is always derivative, which is because everything is real, it's 2 times. What does it imply? The T dot is perpendicular to T because the scalar product is 0. T dot of S is perpendicular to T of S for any S. Okay? This is a standard computation. So it means I can construct 2 vectors if the second one is not of norm 0. I know the first one is not, but so I'm going to set kappa of S, this is the kappa of S, as a norm of this T dot. And this kappa is called curvature as a name. The curvature of C of the curve. And now I need to assume if kappa of S is not 0. This is a number. We will see that it's not a big assumption. I'm going to set T dot of S is kappa of S times N of S. So what do I define here? In fact, I define N with this relation because kappa is just the norm of T star. So T dot. So I define N, and N as of norm, or is of norm 1. And of course, T of S is perpendicular to N of S. Okay. Norm 1, thank you. And then I have 2 vectors in R3 I can construct a third one. We set, so we have T of S, N of S, and I take a third one, which I call B of S, and also normal, so basis of R3. So I started with a curve. I parameterize the curve such that at every place we have one tangent vector which is of norm 1. Then if kappa of S is not 0, I have constructed a second vector which is called N of S. I'm sorry, but it should be in R3. Then there is a third vector which is perpendicular to these two in R3. This, I don't know how to represent it. This is B of S. This triple is called the Freinet frame. And there is a picture in the notes. At every point along the curve, you create a certain frame, so orthonormal basis. Now, just what happens if the curvature is 0? It's not a big problem. It simply means that there is not a canonical choice for N. You have to choose it by yourself. That's it. So if it's a remark, if kappa of S is 0, we can construct. We can construct N of S and the third one B of S. I would say artificially, but this is not a good word, or by hand. What I mean, you don't have a canonical way to do it. You just, if you have a straight line, if your curve is straight, there is no curvature, you need to construct two vectors in the orthogonal plane. You have no specific choice, so you do a choice. You take a decision. And I wrote something more in the notes. Yes. Wait.
Middle board, dollar line.
Set TS is. Oh, yes, thank you. No, wait. Yes, it's a tangent vector. Yes, thank you. Yes. Yes. Yeah. Now, so don't worry about the case kappa of S is 0. You simply have to choose something, while if kappa of S is not 0, the choice is automatic. Now, we have three vectors depending on S. So we can take their derivative, and their derivative can also, they are vectors, they can also be expressed in terms of these three vectors. And this is called the Freinet-Serre formula. So consider T dot of S, N dot of S, and B dot of S. One has. These derivatives are not arbitrary. They satisfy a certain system of equation. So you already know for the first one that you have this relation by definition. N dot, this is an exercise. You can show this is minus kappa of S, T of S, plus a tau of S, S, and E dot. So you have not too much freedom. I mean, they have to satisfy this system. And what is this tau? So we have 2 times the same tau. This is a tau. This is a tau. This tau is called the torsion. So we can express the derivative of these 3 vectors in terms of a linear combination of T, N, and B. Yeah. So it's an exercise to show that these relations hold, and this is called the Frenes-Serre formula. This is called this system Frenes-Serre formula. And why is it useful? You can do you express, for example, the evolution of a particle inside this formalism, which is directly linked to the particle itself. So it's a useful reference system. You know, instead of always working in a fixed reference system, sometimes it's useful to have your reference system following a certain curve, and there is a canonical way to do it. So I put 2 exercises related to this. Again, this is mainly calculus 2, but it's good to know that it exists. The next section is again something in Rn, because the following section is going to be more difficult, but this is for next week. So we do a first version, which is not too difficult. It's about differentiation related submanifold in Rn. So what do I mean by this? We really have a manifold like this inside Rn. So we are dealing really with a classical picture, I would say. And this section is about this. The next one will be an abstract version where you deal with one manifold without embedding. Okay. So we consider smooth manifold. M inside Rn. And the good point with this embedding is that the tangent vectors or any vectors on the manifold, you can really represent them because they are inside something bigger. So consider a vector field in Rn. Remember, in this picture, vector field is really at every point of Rm, you associate just a vector, because the tangent space is Rm itself. So it's just one vector in Rm. So we consider a vector field in Rm, and I call it capital Z, which implies that Zp is just a point in the tangent space of Rn, but this is you can identify it with Rn itself. It's identification. So at every p in Rm, you have just a vector in Rn. Now I want to restrict this vector field to the manifold. So instead of looking at any p inside Rm, I will just look at the p on the manifold. But the vectors can still go in any direction. So if we consider only P belonging to the manifold, we get a vector field. So this is inside, in fact, the definition. We get a vector field. It's called along M. I haven't introduced this. So it means that just the initial vector field, which is defined everywhere, I consider it only for points P on the manifold. And it is still a smooth vector field. What do I mean by this? It's not super precise, but the initial vector field was smooth. So it means if you move from one point to another one, it moves smoothly. Now, when you take the restriction on M, it's still smooth when you go from one place to another one. So there is nothing special. So now, so this is the definition of a vector field along M. We just consider it with P on M. If ZP now is T inside TP of M. So what do I mean? I mean now if all these, okay, it's difficult with this picture. If these vectors, now I need to come to a simpler version. If these vectors are tangent to the manifold and not going in arbitrary direction, so now I consider the case where the tangent vectors, the vectors defined everywhere are tangent to the manifold. So if ZP is inside this tangent space on the manifold, we say that Z is tangent to M and right. So it's an abuse of notation, right? Z belonging to T to curly. Okay, think about it. I'm going to show you. Okay. So we start with the vectors going in any direction in the full space. Then we just consider the vectors which start on this manifold. This is called a vector field along M, but the vector can go in any direction. Now, if the vectors are tangent at every point, they are tangent to the manifold, we say the vector field is tangent to M, and we write this. Why is it a bit an abuse of notation? Because I define this in the abstract framework where it's not represented. But it turns out that because everything is in Rm, when I introduce the tangent space in the abstract version, I use also that if we are in the concrete representation in Rn, we can really deal with vectors. It was a directional derivative. So this is a slight abuse of notation, but in fact, it's correct. So we say that this Z is tangent to M if at every point we have a vector which is really tangent to the manifold. Okay. But now, what is the main difference with the abstract version? So because everything is inside Rn, and in Rn we have a scalar product, the usual, or I should call it, we have an inner product. But it's the same as a scalar product. Same as scalar product. you know what is the scalar product of two vectors in Rn. So clearly, Tp of Rn has an inner product. But it induces an inner product on Tp of n. You shouldn't be surprised with this. You have the usual scalar product in R3. Now, if you consider only vectors on a plane, so it means you consider only vectors, not arbitrary, but which are on this plane, you have the same scalar product for vectors in this plane. That's it. So it induces an inner product on this one, on this on this tangent space at one point. It has a scalar product, which is just the one from Rn, but for vectors which are on this tangent plane. But if we are in this situation, it means M becomes a Riemannian manifold. Yeah, this is not very surprising. Last week, I told you any smooth manifold can be endowed with the structure of a Riemannian manifold. I'm saying the same thing, but in a slightly different framework. I'm saying this for a smooth manifold inside an ambient space. That's it. And we have exactly this scalar product on every tangent space. Okay, but now it means we have, with this scalar product, we have the notion of orthogonality. It means, or it implies that any ZP inside EPM, so any vector can be decomposed, in two vectors. So you have a ZP can be written as ZP prime plus ZP double prime. What does it mean? It means this one is in TP of M, and this one is perpendicular, is in TP of M perpendicular. Indeed, like my umbrella. Any vector can be decomposed into one component on the manifold and one component perpendicular to it. That's it. Any vector starting here has one component on the manifold, one perpendicular to the manifold. That's the meaning. Sorry. Lost my microphone. I hope you can still hear me. If there is anybody, you can tell me if you can still hear me. Okay. We always have this decomposition into one part on the tangent space, and this one is called, it's a normal plane. It's called the normal plane to M at P. It's a plane which is orthogonal. And I will still introduce one notation. I told you this is quite natural. You decompose into one subspace and the ortho complement. Let me just set this ZP prime. I'm going to say that this is, okay, I just defined something. And ZP second prime is, what are these two, pi prime and pi second prime? These are just projections on TP of M and TP P of M orthogonal. I will need this later. So I'm just saying this decomposition is obtained by a projection. Can you, Pratham?
Yeah, I can.
Yeah. Can you turn off your?
Oh, is it on?
Okay, good. Thank you. So I want to introduce this notation, just saying that this component is a projection applied to Z, put everything on the manifold. This takes the ortho complement. That's it. But I will need this in a second. Okay. I told you this shouldn't be too complicated now because we have an ambient space. That's the point. Okay. Now I consider a smooth curve on M. I consider a smooth curve on M. Okay. So it means I consider C from an interval, or I'm lazy. I just write a map of this type. I don't even need to specify an interval. I just want to say I take a T and I go on a curve like this. If I need, I can put an interval, but I don't even need it. Okay. And I consider now, be careful, I slightly change the letter, and I will tell you why. Because I consider Y belonging to this. So from now on, this Y is always a vector field on the manifold, but all vectors are tangent. So I use this notation. It means at every point, the vectors are tangent to the manifold. And Y will be such a vector field tangent to the manifold. Okay. So I can consider the map T goes to Y of C of T. What is this? Oh, that's nice. I look at these arrows which are along the curve, but be careful. At every point, we have a curve. At every point on the curve, we have a vector which is on the manifold, but it doesn't mean it's along the curve. I mean, it doesn't mean they're following the curve. I just mean at every point on the curve, we have a vector which is on the manifold. That's our framework. At every point, we have a vector which is on the manifold. That's the construction. And we can look, of course, at its derivative. And now the derivative is something simple because we are in Rn. Yes. So we let blah, 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 and take the derivative with respect to T. So it means I consider dy of C of dot dt evaluate at T. If I want to be precise, this is the notation I should use. At every T, I have a certain vector, and I consider its derivative. Why it's easy? Easy because of Rn. Remember, a derivative, you need to take two vectors which are close to each other, and you divide by, you take the definition of limit. It's this at t plus epsilon minus this at t divided by epsilon, and take the limit when epsilon goes to 0. You can do it because you are in Rn. So the addition of two vectors is or the difference of two vectors is well defined in Rn. We had a problem a long time ago if you don't have an ambient space. Okay, what is this? It's again a function along the curve, because it's defined at every point along my curve, but this derivative has no reason to be tangent. So we can have vectors which are pointing in any direction in space. They are just vectors starting along this curve, but this derivative has no reason to be on the manifold. Be careful about this. So these vectors are defined for any point on the curve, but they have no reason, to be tangent to M. You can draw this easily. They have no reason to be tangent to M. So what you do in this case, you force them. So we are going to consider, but now I take the same object, dy of c of dot derivative, evaluated at t. How can I force it to be tangent to the manifold? I put this pi prime, because pi prime is the projection on the manifold. So I just take the projection of this vector on the manifold. This one belongs to t ct of m. It's a tangent vector at the point ct. Remember, this is this pi prime, and this is why I introduced it. It is a projection on tp, or t, precisely c at t of m. Okay. Definition, and I will probably stop after this definition. I just recall the framework that Y be a vector field which is tangent to M, C a smooth curve on M. We set. So I give a definition to this object. And it's a strange definition, but it's written like this. It's a capital D Y with a small d t. T, and the definition is precisely this pi prime of d y c of dot t evaluated at t. Okay. And this is called the covariant derivative of y along the curves. Okay, yeah, it's a y, you're right. It's not, it's dy evaluated at the point C. I take the derivative. Most of the time, now, if you are a student, you would write a t here. I don't like it because I want to differentiate a function. Well, if I put a t, it's already evaluated at one point, so the derivative should be 0. But of course, if you put a t here, it's not completely wrong, but it's 50% wrong. So I prefer to put just a dot. But yeah, if you prefer to put a t here and take derivative with respect to t, that's also fine, but then you don't need to write this one. I prefer to just put a dot so that now this is a function. It's a function of one variable. I take the derivative with respect to this variable, and I evaluate at t. But the good point with this derivative, look, it belongs to t, c of t, m. So this covariant derivative is a derivative, and we will study it next week. So we started with a function defined on this curve, always tangent. And when we take this covariant derivative, it's a derivative, but it's projected again on this manifold. So this guy is also tangent to the manifold everywhere. However, in order to define it, you can see I needed to go outside. So it's not an intrinsic picture because I'm using the exterior. I'm using Rn to define the derivative, and then I project. So it's not an intrinsic definition. Even though everything at the end is on the manifold, I needed the outside space for defining this derivative, and that's it. So next week, we will study a little bit this. Still, this is not too difficult. And then we will try to make an abstract version of this, staying only on the manifold, so without this ambient space. That's the final aim. Yes?
Like on the left-hand side of the last equation, it doesn't seem like there is a notation of C of T. So I'm wondering, like, this value is independent of the time?
Yes, this is an excellent observation. I will mention it next week. Okay, the observation is here we have a C. It sounds strange that here we have no C. And indeed, this expression is independent of the choice of C. It's only dependent on the tangent vector. So in fact, what is hidden in this notation, and what is important is the C prime of T, which is a tangent vector. So if you check, on your manifold, you take a tangent vector, you can make many curves which have this point, this vector as tangent vector. And it turns out that this quantity is independent of the choice of the curve, is only depend on this tangent vector. Yes, but we are not here yet. But yeah, there is something independent of C in this notation. Very good. Any other question or remark?